This is Lab 1 constant velocity for Physics 2211 by Nam Lee. So an introduction to this lab, basically the purpose was to show constant velocity when there's no net force acting upon an object, basically just proving Newton's laws, and that if net force is equal to 0, then it should be a constant velocity. And we basically assumed in this experiment that the surface that we rolled our system on would be flat, like perfectly flat, and it was in a straight line path after the applied force, and that there was no resistance, including air resistance or friction. And the ending results, we were able to find that it was proven that Newton's second law was present, basically. So important physics principles that took place, as I mentioned before, are Newton's first law and Newton's second law. An object in motion will stay in motion unless acted upon by an outside force. This remains true when the system or object is also in rest. Unless it is acted upon by a net force of like non-zero, then it should be a constant velocity. So constant velocity is 0, it should stay 0. And with second law, this basically shows that equation that an applied force would result in acceleration and basically change the velocity. And we use the position update formula and the velocity update formula to show this, and this will be present in our code later. So this is a picture of our experiment. We took a video of us rolling a water bottle on a flat table with a meter stick next to it, and we basically observed whether or not it had constant velocity. But however, obviously we can't tell that this is, if it's constant or not, so this is why we use the tracker later on. But the system is the rolling water bottle, and we assumed that there was no too much friction, air resistance, or gravity acting on it. And our initial position was 0 meters and initial time was 0 seconds. So here's a picture of the tracker. All the little red marks are our little tracker positions, and it basically helps us to see the velocity of the bottle as it moves. And the blue line is a calibration to help the tracker to know basically the dimensions that it's working with. So here are the tracker statistics that we found after recording and putting the video into the tracker app. Basically, we set our initial position to 0, and the initial velocity was measured to be 0.366 meters per second only in the x direction, which should make sense because we hope that it would be in a straight line, so it shouldn't be moving in any other direction. And on the right here, you can see that there is a graph, and it shows the video analysis versus the computational model, which we programmed through GlowScript. So as you can see, the blue video version, which we use with the tracker, doesn't seem to be as perfectly straight, and that's obviously because there's different forces that are probably acting on the bottle, and we can't get a perfectly accurate representation of Newton's laws. However, the computational model, which would be quote-unquote perfect, does not have any change in the velocity. It's constant change in position. So what if the x-axis was flipped? This wouldn't change anything regarding constant velocity, because it would just appear that the object would be moving in position in an opposite direction. Basically just it would look backwards, but it would still be moving in a constant velocity because no net force is acting upon the object. And this basically goes with what I said earlier, why does this matter? It doesn't matter what direction it goes in, there should be a constant velocity so long as there is no net force acting upon the object. And here's our GlowScript program. On the left here, you can see we use the position and the velocity update formulas. On the left, they're set over there. And then we also changed the while loop so that t runs only when it's less than 3, because our video and the rolling of the bottle only lasted about 3 seconds. So we wanted to keep it under there and keep as similar to our test as we could. And on the right here, we set our basically our starting position, which I said was 0, 0, 0 earlier, and our initial velocity, and this was found with the tracker also. And yeah. And here's the visualization of the computational model after you ran the program. It would basically just show the ball rolling at a constant velocity over 3 seconds. And here's another closer look at the graph after showing you guys the code. And as you can see a little closer, that red computational model is much more accurate in showing a constant velocity than our reality version. And some possible errors that could have contributed to this were human errors, like not perfectly, pushing the bottle in a straight line, and also friction air resistance were definitely probably acting on the bottle. And also coding, there could have been some coding issues as we would not have done it perfectly.